Topic 7D, two-dimensional finite difference method. In this lecture, we're going to build on previous lectures and show how to build derivative matrices on a two-dimensional grid instead of a one-dimensional grid. I am certainly going to give examples for the derivative matrices, examples for applying it to solve two-dimensional problems will be in the following lecture and not here because this one just got to be a little bit too long. I'll first start off talking in general about the finite difference method in two dimensions to generalize some of the concepts you already know. And then after that, our big task is to build these derivative matrices that are now operating on a two-dimensional grid. And there's two ways of doing this, where we can use a collocated grid, meaning all of your functions are defined to be at the same point. And then there's the staggered grid in two dimensions where you have two or more functions and they're residing at different points. We're staggering them to improve our finite differences, like in our previous lectures. Once we get through that, some final notes on derivative matrices, and then how to generalize this, or to teach you how to use your two-dimensional derivative matrices for solving 1D problems. Now, why is that important? Because I don't want to have to write two different functions, one to create derivative matrices for a 1D grid and another to operate on a 2D grid. It turns out we can generate those same derivative matrices just using our 2D code. And in fact, while we're not talking about it here, but if we were to jump into 3 dimensions, you can use that same function to generate derivative matrices for 2D grids and 1D grids. And it's always good practice to do things with just one function if you can. On to some just general concepts about the finite difference method for two-dimensional problems. We went through this before, but I'd like to go through this again just as a way to look at our matrix and try to interpret what the rows and columns are doing. So we start off on the left just with a system of 3 equations and 3 unknowns that we cast into matrix form. So it turns out we can ascribe some meaning to the rows and columns. And for the rows, we will interpret this as the equation for x, the next row is the equation for y, and the next row the equation for z. Now, from a purely mathematical perspective, that first row has nothing more to do with x than it does y and z. This is just a convenient way to think about it. Now, when we're implementing the finite difference method, there will be a finite difference equation hiding behind each point, and maybe that makes a little bit more sense that finite difference equation would be written for a specific point on the grid. But interpreting our rows this way is very helpful in finite difference method. Last, the columns. The first column will be the relation to x, second column relation to y, and the third column relation to z. So we could go pick a parameter, a23. This parameter is residing in the equation for y and describes how y is related to z. And we could do this for each parameter in that matrix. Just like we said for one-dimensional functions, a real function contains an infinite amount of information that we can't store. We have to break space up into small cells. But even within one of those cells, there is still an infinite amount of information. So in fact, we can only store the function at one infinitely small point inside each one of those cells. So if we were to try to visualize how the finite difference method stores a function, it would look like this last thing here. And well, we tend to draw it more like one of these first ones, but really in memory, this last picture is the most representative of what's actually stored on a finite difference grid. We don't know the value of the functions between those points. Now we can do a good job interpolating, but the reality is we just don't store that information and we don't know it. And we try to get away without knowing it as much as we can. So if we look at one cell, it now has not only a delta x, it has a delta y. So it has a width and a height. Even though we're only storing the function value at one point, and in this case in the middle, And it's not necessarily that we store the function at the middle. It could be at any place within this cell, but it's common to put it in the middle. So our cells now have two grid resolution parameters, a delta x and a delta y. And they can be different. We tend to want them to be as similar as possible, but we can make them different, and most of the time they are slightly different. And there's reasons for that we'll get into when we start simulating devices in the next lecture. So even though we're moving into 2 dimensions and we're storing our unknowns in a 2-dimensional array, we still store all of them in a 1-dimensional column vector. Now that's easy to imagine for 1D systems because we already have a 1D array. But with a 2D system, even though we have a 2D array, in memory it's stored serially anyway. So maybe picture that. But what we do is we raster through this in some way, and then just list all of those in a 1-dimensional array. We call that reshaping. On the next slide, I have a way to visualize this if you're struggling with this concept. So imagine we have unknowns stored in a 2-dimensional array. Now imagine we run a string through them and then pull that string straight. We would end up with a 1-dimensional array of all the elements in the 2D array. And by the way, in MATLAB, that's real easy to reshape any dimensional array to a column vector. We just say E parenthesis colon, and that reshapes an array E always to a 1-dimensional column vector. And so that might look something like this. So typically we'll draw something, reshape it to a column vector. We'll do all of our linear algebra stuff. We'll get an answer. That answer comes out in a column vector. And then what we want to do before we can visualize it is reshape it back to a 2-dimensional array. And we can use MATLAB's reshape command to do that. And in fact, we can toggle back and forth, go from 2D to 1D, back to 2D, and so forth. We use the column vectors when we're doing linear algebra stuff. We reshape back to the arrays when we want to visualize and try to interpret our answer. There's 2 types of grids that we'll talk about in 2 dimensions. We have what's called a collocated grid. That means all of the functions are stored at the same points on the grid. So we might have multiple unknowns, f, g, h, and more, but we're always storing them at the same points. In which case, the finite differences we have written on the slide are the finite differences that we use. They're all central finite differences, and they're all spanning 3 cells, calculating the derivative or the second-order derivative at the midpoint. So I would recommend pausing the movie here and looking at those finite differences and try to understand what's happening for x and y derivatives. The y derivative is new because we have an added direction here. The second type of grid is called a staggered grid. And just like in 1 dimension, when we had multiple variables, we found that it's usually good practice to stagger our multiple variables. That way we're calculating our finite differences over a shorter span on the grid, and we get better accuracy. However, it required us to stagger where our functions are. So looking at this first grid, we have an unknown f stored at these blue points. And if we use the finite differences shown over to the left here, and if we interpret these as central finite differences, what you'll see is that they're calculating the derivative at the midpoint between the function values f. So if we look at this first finite difference, we see an f at I plus 1 minus f at I. That means this finite difference exists right here at the midpoint between those two f's. And we can look at the y derivative, and we can see this finite difference would exist at the midpoint between two function values f. So we're doing this probably because if we have another unknown here, it's residing at these 2 points. Then we can also do our derivatives really in the other direction. These first ones we called right-hand derivatives, because when we're calculating a derivative in one cell, it's actually reaching to the function value to the right to calculate the finite difference. Whereas over here, we're calculating a finite difference associated with this cell, but we reach to the left to get the next value. But it's still calculating those central finite differences in the midpoints, but that midpoint is to the left. Whereas right-handed derivatives, that midpoint's to the right of the function value. So that's the background. No worries if you're still a little bit confused. We have lots of slides ahead to explain these finite differences and how we build the derivative matrices. So right now we're talking about a collocated grid. That's a bit easier than the staggered grid. And we'd like to know about the derivative matrix for calculating a derivative in the x direction. So we define a grid that's 4 points wide, 3 points tall. Why did I choose that? That's just the mood I was in, but we can apply the same concept to any size grid. So for a collocated grid, we have the finite difference that we're using at the bottom. And notice it's f in the next cell minus f in the previous cell divided by 2 times the grid spacing. That means we're actually calculating the derivative at fi. So let's go one at a time here. And we write our finite difference equation for every single point on this grid. There's 12 points total. So we have 12 equations. What we want to do now is go one at a time and explain what's going on. So we're writing our finite difference equation for f11. So here's our finite difference equation. Looking at the finite difference equation at the bottom, we see it's fi plus 1. So in that case, that's f21 minus f at I minus 1. So it's the f out here, which doesn't actually exist. So that's why we see f21 minus 0. We're using Dirichlet boundary conditions. Divided by the grid spacing, 2 delta x. Why 2 delta x? Because our finite difference is actually spanning 2 delta x's. But the finite difference exists at the midpoint. Now we move over to the next point. So it's f31 minus f11 over 2 delta x. And of course, that's calculating the derivative at the point of f21. No boundary conditions were needed because we didn't have to reach to outside of the grid. We move over to point f31. So we interpret this as the finite difference equation for f31. Well, that is simply f41 minus f21. It spans 2 delta x, so we divide by 2 delta x, and the finite difference exists at point f31. Now we move on to the finite difference equation for f41, which is the function value out here, which does not exist, so we just put a 0 in for Dirichlet boundary conditions. So it's the 0 minus this function value divided by the spacing 2 delta x. We go on to the next point, the finite difference equation for f12. Well, it's f22 minus a function value from outside the grid, which doesn't exist. We put a 0 in there, divide by 2 delta x. That's calculating a finite difference that exists at the point f12. So hopefully you're getting the pattern here. We move to the next point, f32 minus f12 divided by 2 delta x, and the finite difference exists at the point f22. And we go on to the next point, f42 minus f22 over 2 delta x. Now we're at the boundary again. So we have a 0 in our finite difference equation, which is the value outside of the grid, and we force it to be 0 if we're using Dirichlet boundary conditions. Now we move down to the next row. We're writing the finite difference equation for point f13. But this also has a boundary condition problem on the left, so we put a 0 in that finite difference expression when we need to access something outside the grid. So it's f23 minus the 0 divided by the spacing. f33 minus f13 over 2 delta x, that exists at f23. f43 minus f23 divided by 2 delta x, and that exists at f33. And the last one, a field from outside of the grid that we write a 0 for, minus f33 divided by the grid spacing. So we've taken this finite difference expression at the bottom of the slide and wrote it for every point on the grid. At some points where we had to reach to the outside, we use Dirichlet boundary conditions and just put a 0 in. So now we have this large set of finite difference equations. We would like to put them into matrix form and figure out what is that big square matrix that we would pre-multiply our column vector of the function values, reshaped to a 1D array. What goes in here such that we get this answer? So we're storing our finite differences in this column vector. Those are what we just derived. I factored out the 1 over 2 delta x. And so we need to fill in this matrix such that we get this answer. So this is what it looks like. We notice in the first row, there's only an F21. So there's a 1 in the column corresponding to F21. In the second row, there's an F31 and an F11, a minus F11. So we have a 1 in the column corresponding to F31 and a negative 1 in the column corresponding to F11. And so we can go each row at a time and make this same argument. And I definitely recommend pausing the video and looking at each row and showing how the ones and zeros and negative ones are placed into that big matrix. When we're done this, that big matrix, also pre-multiplied by the 1 over 2 delta x, that is our derivative matrix that would calculate a derivative in the x direction of that two-dimensional function. Now let's look at the derivative matrix for a collocated grid, but this time for the second order derivative. And what you'll see is this is very similar, the same steps we just went through. We just have a different finite difference equation because it's approximating a second order derivative instead of a first order derivative. So here's the same grid, a new finite difference equation, which is of course approximating a second order derivative. So we write that finite difference equation once for each of the 12 points on this grid, and we end up with a big set of finite difference equations. And again, we can go one at a time and look at these finite difference equations. So here we're writing the finite difference equation for the point 1, 1, where f11 is stored. We want to evaluate the second order derivative there. So it is this function value minus 2 times this function value plus this function value. But of course, since the first one's outside the grid, we put a 0 in because we're using Dirichlet boundary conditions. And so we end up with a 0 minus 2f11 plus 2f, sorry, let me just start over with this. We have a 0 minus 2f11 plus f21, all of that divided by delta x squared. So that approximates the second order derivative at point f11. So we move to the next point. And we're evaluating the finite difference at point f21. So we call this the equation for point f21. And so it's f11 minus 2f21 plus f31, all divided by delta x squared. No problems because there was no boundary conditions we had to sort out. We move on to the next point. f21 minus 2 times f31 minus f41 divided by delta x squared. That's the finite difference equation at the point f31. Now at the right-hand side of the grid, we have another boundary condition problem. So we put a 0 in since we're using Dirichlet boundary conditions. So we end up with f31 minus 2 times f41 plus 0 because the f51, if you will, would be outside of the grid. Next point, we move down to the next row, and we have a boundary condition problem here as well because we're reaching to the left, and we have a 0 in the finite difference equation. This is the finite difference equation for the point f12. Next line, no boundary condition problem. I'm going to start moving a little bit faster. Hopefully you're getting the pattern by this point. Move on to the finite difference equation for f23. And then for finite difference equation for point f42. And we have a boundary condition issue here because we're reaching to the right. And so in the place of f52, which doesn't exist, we put in a 0. And we move to the last row. We have a boundary condition problem again on the left because there is no F03. Finite difference equation for F23, finite difference equation for F33, and finally the last finite difference equation for point F43. And we're reaching to the right outside of the grid. There is no F53, so we put in a 0 for it. So there we are with our large set of equations. Again, we would like to put this into matrix form. And first, on the right, we fill in our column vector with the answers that we want to get. And on the left, we write a big blank matrix, pre-multiplying our column vector of function values, reshaped to a 1D array. And we ask ourselves what has to go in this big blank matrix such that we get the answer on the right, which is our finite difference equations that we just derived, one for every point on the grid. Well, here's what it looks like. Let's jump to the second row here. We have an F11 minus 2F21 plus F31. So we have a 1 in the F11 column, a negative 2 in the F21 column, and a 1 in the F31 column. Now on the first row, we sort of want to have a 1 over here, but due to the boundary conditions, there's a 0. So we only have a minus 2F11 and an F21, and that's the two numbers sitting here due to our Dirichlet boundary conditions. So we can look through this one row at a time and figure out what goes in the matrix on the left. I definitely recommend pausing the video and working through this on your own, one row at a time, to see that the numbers in the big matrix to the left really do reproduce what's in this final column vector. After we do that, we call this big matrix our derivative matrix for second order derivatives, and don't forget to include this 1 over delta x squared. That has to multiply everything in this matrix. Without that, it's not a correct matrix. So we already have two of our derivative matrices for the collocated grid. Now on to the derivative matrix for a y derivative. So now we're taking derivatives in the vertical direction. Let's see what happens. So we have the same grid we did for our x derivatives, but we have a slightly different finite difference equation. Notice it's the j array index that's changing now. So we're actually we're spanning in the vertical direction now. But the procedure we did before, we're going to follow exactly. We're going to work through this grid one point at a time and write that finite difference equation for each point on the grid. When we do that, we get this large set of finite difference equations that we will again go through one at a time to explain where they're coming from. First thing, we need to write the finite difference equation for our very first point, F11. So we would call this first finite difference equation the finite difference equation for point F11. And what we see is that it will be F12 minus what would be an F10, but that doesn't exist. We're using Dirichlet boundary conditions, divided by the spacing 2 delta y. So that's what's over here, an F12 minus a 0 due to the Dirichlet boundary conditions divided by 2 delta y. Then we move on to the next point. A similar thing is happening here. We're reaching outside the grid on the top. That term doesn't exist. We will need to use Dirichlet boundary conditions. So our finite difference equation is just F22 minus what would be an F20, but that doesn't exist. We just put in 0, divided by the spacing 2 delta y. So in fact, all of these top points have that boundary condition problem on the top. We can move to the finite difference equation for F31 and the finite difference equation for F41. At this point, we come back around to point F12. So similar to the x derivative matrices, we're rastering through our grid, writing the finite differences in the same order that we did before. It's just that the finite differences equations are different. They're reaching to different points in the grid. So here we are writing the finite difference equation for point F12, and that answer is F13 minus F11 divided by the grid spacing. And of course, that finite difference exists at the midpoint at F12. Move on to the next point, f23 minus f21 divided by 2 delta y because we're spanning 2 points. Finite difference equation for f32. Finite difference equation for f42. Now we move to the last row. We have another boundary condition problem because now we're reaching below the grid. In this case, we would like to access an F14, but that does not exist. So using Dirichlet boundary conditions, we simply put a 0 in the place of it. So we have our 0 minus F12 divided by the spacing 2 delta y. And of course, all of the remaining points on this row, we're going to have that same boundary condition problem because they're always reaching below the grid. So we have our 0 minus f22, but of course that's calculating a finite difference that exists at f23. 0 minus f32, and of course that finite difference exists at f33. 0 minus f42, which is the finite difference equation at point f43. So on the right, we have all of our finite difference equations. The finite difference equation written once for every point on the grid. We would like to figure out what our derivative matrix looks like. So we start off by writing a big blank matrix that pre-multiplies our column vector F. And if this is correct, we want that to give us the answer on the right, which are all of the finite difference equations that we just wrote. So here's what goes in that matrix. And this looks a little bit different than the x derivatives. So in the first row, we just have an F12. So there's actually a 1 way over here. This first position was F11, 2-1, 3-1, 4-1, and then finally F12 in this column. So that's why the 1 goes there. And let's work down. Let's look at the fifth row now. We have an F13 minus F11. So we have a 1 in the F13 place and a minus 1 in the F11 column. I recommend pausing the video again here and going through this row by row and seeing how the finite difference in that last column vector on the right is calculated on the left by proper position of the zeros, ones, and negative ones in that big matrix on the left. So that big matrix on the left, that is our derivative matrix that would calculate a derivative in the y direction. And our final derivative for the collocated grid, it'll look exactly like the other one, with the one exception being a different finite difference equation, but we'll raster through the grid in the same way and construct the derivative matrix in the same way. We have the same grid, different finite difference approximation now. And we're changing the indices on J, which is the vertical position. So we're doing a y derivative. So we take that finite difference expression and write it at every single point in our grid. And we get a big set of finite difference equations. Like before, we'll go through these one at a time. The first point, which is reaching above the grid, so there's a boundary condition issue. We're not storing F10, so we set it to 0 following our Dirichlet boundary condition rules. So we'll have our 0 minus F11 plus F12 divided by delta y squared. So delta y is our grid spacing here. Move on to the next point. We have a similar boundary condition problem because it's reaching above the grid. So we just have the 0 minus F21, minus 2 times F21 plus F23 divided by delta y squared. Move on to our finite difference equation for F31. Still have a boundary condition problem. Move on to our finite difference equation for F42. Still have a boundary condition problem because we're reaching above the grid. When we're done here, we move to the next row. Here's our finite difference equation for point F12. There's no boundary condition problems here. So this is simply just F11 minus 2 times F12 plus F13, all divided by delta y squared. Here's our finite difference equation for F22, finite difference equation for point F32, finite difference equation for point 42. Now we wrap around to the next row, and we're back to having boundary condition problems again. We would like to access F14. That doesn't exist, so we set it to 0 in the finite difference equation. So we still have F12 minus 2 times F13 plus the 0 divided by delta y squared. Here's our finite difference equation for F23, finite difference equation for F33, and our finite difference equation for F43. And so we end up with our giant list of finite difference equations, one for each point in the grid. And now we're at the point where we would like to figure out what our derivative matrix looks like. So we start off with a blank derivative matrix, pre-multiplying our column vector of function values. And if whatever's in this matrix is correct, it should give us this answer. This last column vector is all of the finite difference equations that we just wrote. And if we do it correctly, it looks like this. So I would recommend pausing the video here, looking at the rows one at a time, and understanding how the numbers that we've put into the derivative matrix do give us the answer that's on the right-hand side here. And don't forget about the 1 over delta y squared on the outside that I factored out. If we do this, what we're left with is our derivative matrix for the y direction for the second order derivative. To really fully learn this, I highly recommend going through the same procedure for different size grids and see where all the numbers end up lying. And once you get the pattern, you'll be able to write a function in MATLAB to build these derivative matrices for you. And of course, once you have that, solving new differential equations becomes very, very easy. So it's a very powerful function to write. Now we need to talk about derivative matrices when we have a staggered grid. And before we get to the specifics of the staggering, that's really application driven. We'll have to know what equation it is we're solving and what variables are involved to do the specifics of how the staggering works. But before that, we can in general talk about derivatives that are right-handed or left-handed. Does the derivative reach to the cell to the right or the next higher array index cell to calculate the derivative, or does it reach to the left? So right now we're going to build derivative matrices that reach to the right, and we call that a right-hand derivative. And so we will be building right-hand derivative matrices. So in this case, we're in the x direction. So I chose a 3x3 grid because I guess that's the mood I was in. And here's the finite difference equation that we want to write once for each point. Now notice the array indices on I. We're changing the array indices on I because we're taking a derivative in the x direction. But notice we have an I plus 1 minus an I. That's calculating the finite difference at the midpoint between these two values. So if we're looking at these 2 points, we're calculating our finite difference right here at the midpoint. And you'll see this conveyed when we go through these one at a time. So we take this finite difference equation, we write it for each of the 9 points in this grid, and we end up here. So let's look at these one at a time. So we are highlighting the 2 points that we're using to do our finite difference, and the arrow is telling us where the finite difference is calculating the derivative. We still interpret this as the equation for F11. However, it's calculating the derivative at the midpoint. So in terms of array indices, we still write it with an F11 here. However, that derivative itself exists at the midpoint between the two. So you could think of it as F1.5, 1. But since those are array indices and not positions in x, we have to leave them integers. Okay, so in this case, we have an F21 minus F11 divided by the grid spacing, which is just delta x now because we're only spanning one cell. This is very different than with a collocated grid when we were spanning 2 cells, which is why if you can get away with this, it's a more accurate approach for implementing the finite difference method. Let's move on to the next point. Here we're writing the finite difference equation associated with F21, but it reaches out to F31, so our finite difference is F31 minus F21, which calculates the derivative at the midpoint between those two functions. So what happens next? We're still writing a finite difference equation at cell 31, so it's the equation for F31. However, we'd like to be accessing an F41, and we'd have an F41 minus F31 divided by the spacing. However, that's outside our grid, so using Dirichlet boundary conditions, we put a 0 in here. So we're just left with 0 minus F31 over delta x. And that's how we handle the boundary condition. Notice we did not have a boundary condition at the left-hand side of the grid. Due to the staggering, we only have boundary condition problem at one side of the grid for this. Okay, on to the next point. We don't have a boundary condition problem here because we're always reaching to the right because we're talking about right-handed derivatives. So here it's F22 minus F12 divided by the spacing, delta x. Our equation at F22, it's F32 minus F22, calculating the derivative at the midpoint. No boundary condition problem. The last cell, we have a boundary condition problem because we would like to access an F41, but that doesn't exist. We'll set it to 0, so we have a 0 minus F32 divided by the delta x. Now we're writing our finite difference equation for F13, and so that's F23 minus F13, the finite difference exists at the midpoint. No boundary condition problem. F33 minus F23 gives us our derivative at the midpoint, and this is the finite difference equation for F23, no boundary condition problem. And of course, the last point has a boundary condition problem because we would like to access an F43, but that doesn't exist. So we've now written for all 9 points in this grid our finite difference equations. And we do the same procedure to figure out what the derivative matrix looks like. We start off with a big blank matrix, multiplying our column vector of f's, and we want to fill in numbers here such that we get these answers on the right, which are our finite difference equations that we wrote once for each point on our grid. And that's what it looks like. And this looks pretty similar to the derivative matrices we saw for our one-dimensional grid. There's an exception here. We've got a 0 interrupting our diagonal of 1s and another 0. And in fact, if the grid were larger, we'd see more zeros down that row. So I recommend pausing the video, going through this one row at a time, and seeing how each row on the right is represented by numbers over here. So we'll do a few here. The very first row, we have an F21 minus F11. So we have a positive 1 in the F21 column and a negative 1 in the F11 column. Let's jump down to this row. We have a 0 minus F32. So we have a minus 1 in the F32 column. And then, of course, there's a 0, so nothing else appears in that row. So when we've done this, we've built our derivative matrix for doing a right-handed derivative in the x direction. Now, since our derivatives look different left and right, I have the f superscript, and later on we'll have a g superscript. And so we're using f and g to represent right and left. Maybe I should have used an r and an l, but I decided to use f and g here because it just made more sense since we're taking derivatives of functions. So that's our derivative matrix in the x direction for right-handed derivatives. Now, to build this for larger arrays, here's the rules of thumb that you'll need. We always have these two same diagonals. And so when I build these matrices, I'll go ahead and just insert all negative ones down the center diagonal and all positive ones in that upper diagonal, and then go back and fix them. And where do I insert them? Well, you'll notice they're spacing. They're big nx apart. That's the width of our grid. and that would continue all the way down. So we can go back and just insert zeros where we accidentally put in ones, and we would have a correct derivative matrix. Another thing to notice we're only dividing by delta x. We're not dividing by 2 delta x anymore. Now we want to build the derivative matrix still for a right-handed derivative, but in the y direction, the vertical direction in our grid. So we have our same 3 by 3 grid, and now here is the finite difference approximation we'll be using. Notice it's the j index now that's changing. And also notice that this exists at the midpoint between j plus 1 and j. So if we are calculating our finite difference for these 2 points, the finite difference itself, the derivative, will be evaluated at the midpoint. So if we write that finite difference equation for each point on our grid, we end up here. And like before, we'll highlight these one at a time, but hopefully by now we can move a little bit faster. So we're writing our finite difference equation for the point f11, and our finite difference will be f12 minus f11 divided by the spacing delta y. Just one cell now delta y, not 2. So again, this is a better derivative to use than on the collocated grid because the points are tighter up against where we're evaluating our derivative. And it exists at the midpoint. The little blue arrow is saying where we've evaluated our second order derivative. No boundary condition problems on this side of the grid. You'll notice the boundary condition problems happen at the bottom of the grid now. But like the x derivative, the boundary condition problems are only at one side. All right, let's move on to the finite difference equation written at point f21. And so that'll be f22 minus f21 divided by the spacing delta y. Here's our finite difference for the point f31, and it's f32 minus f31 divided by delta y. Now we move down to the next row. This is the finite difference equation written at the point where f12 is, but it evaluates the derivative at the midpoint between f12 and f13. So it's f13 minus f12 divided by the spacing delta y. Same story for the equation written at the point where f22 exists. Here's the finite difference equation for point f32. And now that we're at the bottom of the grid, now we have the boundary condition problem. We're trying to access an f14, but of course that doesn't exist. So using Dirichlet boundary conditions, we just put a 0 in its place. So now we have 0 minus f13 divided by the spacing delta y. All points along the bottom have the same boundary condition. So we're going to have a 0 minus f23 over delta y. We're writing that finite difference equation for point f23, but it's actually evaluating the derivative slightly outside the grid. And then the last point, 0 minus f33 divided by delta y. So we have written the finite difference equations for every point on the grid, and we would like to figure out what the derivative matrix looks like that does that. So we start off with a big blank matrix that pre-multiplies our column vector of function values, and we want to know what numbers go in here such that we get this answer after doing the multiplication. And of course, in that column vector is all of our finite difference equations that we just wrote. So here's the numbers that we insert in there. I recommend pausing the video and going through one row at a time to see how the numbers inserted in the matrix in the left really do give us the answer that we have on the right. After doing that, this, and also being pre-multiplied by 1 over delta y, but this big matrix is our derivative matrix, right-handed derivative matrix in the y direction. So for larger grids, let's look at the anatomy for this. We have all negative ones going down the center diagonal, and all ones going down another diagonal that's actually big NX shifted over. So whatever NX is, you know where to place that next diagonal. And as far as the boundary condition goes, we can just insert those diagonals. We don't have to go back and fix where there was zeros that occurred when we had the x derivative. We had some zeros in this diagonal, but this diagonal is actually over here at the time. We don't have to do that. We can just insert two diagonals and we're done. All right, our second to last derivative matrix. This is a lot of work, isn't it? So this is a left-handed derivative matrix in the x direction. So we have our same 3 by 3 grid. Here is the finite difference approximation that we'll be using. Notice it's the index on I that's changing. And also notice we used to have an I plus 1 minus an I. Now we have I minus 1. So we're actually reaching to the left here, which is why it's called a left-handed finite difference. So let's write this for each point on the grid. And if we do that, we get a set of 9 equations. Let's go through these one at a time. So first, we're in the cell containing G11, and we would like to have a G11 minus a G01 divided by the spacing delta x. But of course, the G01 doesn't exist. Using Dirichlet boundary conditions, we'll have a 0 in its place. So it's G11 minus the 0 over delta x. I'll compare again. Compared to our collocated grid, we had to span 2 points across the grid to calculate this finite difference. Now we only span 1, so it's a better way of doing it because the points that we're using to evaluate the derivative are tighter up against where we're evaluating the derivative. And where is that derivative evaluated? At the midpoint between G01 and G11, which is right here, a little bit outside the grid. Now we move to the second point. We're writing our finite difference equation in the second cell where G21 exists, and it's G21 minus G11 divided by the spacing delta x. And of course, the actual finite difference that we calculate ends up calculating the derivative right here at the midpoint between G21 and G11. Move on to our finite difference equation for G31. This is the last point on the right-hand side of the grid, but since we're reaching to the left, there is no boundary condition problem. It's just G31 minus G21 divided by the spacing. Okay, we come back around to the left-hand side of the grid, so we have a boundary condition problem at this side of the grid. And so it's G12 minus what we would like to be a G02, but that doesn't exist. And so we put a 0 in its place. So it's G12 minus 0 divided by the spacing delta x, and it evaluates the derivative just slightly to the left and outside of the grid. Move over to the center point in our grid, G22. So it's G22 minus G12 divided by delta x, which makes that derivative evaluated at the midpoint between G22 and G12. Now we're at the far right point on the grid. No boundary condition problem because we're reaching to the left for our finite difference. So it's just G32 minus G22 divided by the spacing delta x. Back to the left side of the grid where we have a boundary condition problem again. We'd like to write this as G13 minus G03, but the G03 doesn't exist. We put a 0 in its place for Dirichlet boundary conditions, and we just end up with G13 minus 0 over delta x, and it's evaluating that derivative here, just slightly to the left of the grid. Finite difference equation for G23, which is G23 minus G3. It's G23 minus G13 divided by delta x. Finite difference exists at the midpoint between those 2 points. And the same argument for the last point. G33 minus G23 divided by delta x, making the derivative exist at the midpoint between those 2 points. Well, we have our set of 9 equations. What does the derivative matrix look like? So we'll write a big blank matrix equation where we leave our derivative matrix blank. It's pre-multiplying our column vector of g's now. That's to remind us we have left-handed derivatives. And we would like to fill in numbers here such that we get this column vector on the right, which of course is the finite difference equations that we just derived. with the 1 over delta x factored out. So what goes in that big blank matrix? This is what it looks like. This looks rather similar to our right-handed derivative in the x direction, except we had, for the right-handed derivative, we had positive ones going down this +1 diagonal and negative ones down the center. Now look what's happening. We have positive ones in the center diagonal and negative ones in the lower diagonal. And there's also these little corrections that we'll have to go back and do. We'll talk a bit about that at the end. But I recommend pausing the video, looking at the numbers in this matrix, and seeing how they recreate our finite difference answers on the right. So if we do this correctly, that is our derivative matrix for a left-handed derivative in the x direction. We can summarize this by talking about the anatomy. We see two diagonals. We have all ones going down the center diagonal and almost all ones going down the lower diagonal. So when I build these, I insert all negative ones and then go back and fix where I've goofed. And you can see that the spacing between these corrections is nx. That's the number of points wide the grid is. And we're doing that because we're using Dirichlet boundary conditions. Finally, the last derivative matrix that we'll discuss. It's another left-handed derivative matrix, but this is in the y direction, the vertical direction through our grid. We'll use the same 3x3 grid. We just have a new finite difference equation. Now notice we're changing the j index. So it's g in the same cell minus g in the previous cell, but in the y direction. So if we were looking at this finite difference with these 2 points, we would be evaluating that derivative at the midpoint. So if we write that finite difference equation for each of those 9 points, this is what we get. So like before, we'll go through these one at a time so that we can see each one. You could pause the video and see what's going on for any of the steps that you want. Okay, now we're writing the finite difference equation for the first point on the grid. That's where G11 exists. And so our finite difference would be G11 minus G10, which is of course outside the grid, does not exist. So we put a 0 in its place using Dirichlet boundary conditions. So we just have G11 minus 0 divided by the spacing delta y. So we have our boundary condition here at the top of the grid. Remember when we did the right-hand derivative matrix for the y direction, we had the boundary condition problem at the bottom of the grid. So due to the staggering and the handedness of these matrices, they have the boundary condition problems at the opposite side of the grid. Let's move to the second point. G21 minus what we would like to be a G20 divided by the spacing delta y. But of course, G20 doesn't exist. We set it to 0, and we just have a G21 over delta y. And the last point that we'll have that has a boundary condition problem, G31 minus G30, which does not exist. So we put a 0 in its place. So we have a G31 over delta y. And of course, all of these finite differences existed at a half grid cell above the top of the grid. Now on to the finite difference equation for G12. And this is G12 minus G11 divided by the spacing delta y. And of course, that's evaluating a derivative that exists at the midpoint. That's where the arrow is pointing. Now our finite difference equation for G22, which is G22 minus G1 over delta y. And it exists at the midpoint. Finite difference equation for G32, which is G32 minus G31 divided by the spacing delta y. And the last row, our finite difference equation for G13. And that's G13 minus G12 divided by the spacing delta y. G23 minus G22 over delta y. That's our finite difference equation for point 23. And it exists at the midpoint between those 2 points. And our very last equation, it's the finite difference equation for G33. and it's G33 minus G32 divided by the spacing delta y. So we have our set of 9 finite difference equations. Now we would like to figure out what the derivative matrix looks like to do this. So we write a matrix equation with a big blank matrix, pre-multiplying our g's, reshaped to a column vector, and that has to equal a column vector containing the finite difference equations that we just evaluated. So we ask the question, what goes in here that would give us this answer? And this is what it looks like. Recommend pausing the video and looking through this row by row to justify why these numbers are what they are to get the answers we see on the right-hand side. After we've done this, we have constructed our derivative matrix, our left-handed derivative matrix in the y direction. And looking at the anatomy of this so that we know how to build it for any size grid, we will always have ones going down the center diagonal, positive ones, but we're going to have negative ones going down a certain number diagonal below that. And it turns out this distance is big NX. And of course, don't forget to divide everything by delta y. So this is our hint for building our derivative matrix, left-handed derivative matrix in the y direction. We simply just insert 2 diagonals. There's no need to go back and correct for any kind of boundary condition problems. Some final notes on the staggered grids. On this slide, I'm just summarizing the anatomy of all 4 derivative matrices that we had to construct for our staggered grid. So there's no new information on the slide, just a summary in one place. So when you're writing your MATLAB code, you can refer to this slide rather than have to page through everything. Here's what the matrices look like for a 4x4 grid. Notice now it's even more obvious how many zeros there are. This is another justification that we really want to do sparse matrices here. In fact, we absolutely must use sparse matrices or you'll easily run out of memory. The larger the grid, the greater the fraction of these containing all zeros. We don't want to store those zeros as double floating points. So always at every step, use sparse matrices. Don't at any point store these as a full matrix or you'll run into trouble. Some skills you'll need for building these matrices, one is inserting diagonals and declaring sparse matrices. MATLAB is very good about sparse matrices. We need to do little more than just say, hey MATLAB, this matrix is sparse, and then we just do our normal algebra with it, and underneath the hood, MATLAB recognizes that it's a sparse matrix and it's calling algorithms optimized for sparse matrices, which is another neat discussion, but it's not something that we have to really deal with at this point. So we declare the size of the matrix. We'll make a sparse matrix of all zeros. We'll create a one-dimensional array containing all ones. Those are the numbers that will go down the diagonal. They don't all have to be ones. We could create a one-dimensional array that goes 1, 2, 3, 4, or whatever numbers we want to. This last command is what inserts the diagonal into a sparse matrix, so SP-diags. We give it the array of numbers that we want to insert in the diagonal. We tell it which diagonal to insert into, and we give it the matrix to start with. So at first we just pass it the 0 matrix, and it inserts those ones down the center diagonal of all the 0 matrix, and we end up with this. Well, we could do something else too. We could insert the diagonal twice. We could insert negative ones and positive ones in the negative 1 and positive 1 diagonal, and we would end up with a matrix that looks like this. So SP-diags is really your workhorse function for building these derivative matrices. I won't spend a lot of time on this slide because this is something we've discussed before, but I'm covering here the transpose operation, the Hermitian transpose, which is a transpose and then a complex conjugate. But what I wanted to point out is these staggered or left-handed, right-handed derivatives, they're related. If we've calculated a right-handed derivative matrix in the x direction, we can usually immediately calculate the left-handed derivative matrix. It's just the negative Hermitian. And that holds for most of the boundary conditions I've tried. When I build in Newman boundary conditions, I notice that this does not work. There might be another relation there. It's just not something that I've investigated. So this halves your work. For just Dirichlet boundary conditions, this works fine, and it halves your work. You really only have to build the right-handed derivative matrices, and you can calculate the left-handed ones just with the negative Hermitian transpose. So that's very useful. One final slide, and I hinted to it in the beginning, but we don't have to write separate functions to build derivative matrices for 1D grids and then 2D grids and then 3D grids. I'm only going to show how to get the 1D derivative matrices from a function that would give you derivative matrices for 2D grids. For the most part, if you write a function to build the 2D derivative matrices, it just works really without modification. The one thing that we have to keep in mind, though, we have to do a special check when we're doing the X derivative matrices. If the size is only 1, we need to make an all zeros matrix. If you don't do that, you'll end up with a 1 or 1 or 2 diagonals in your matrix. So for when nx is just size 1 and it's also an x derivative, your derivative matrices should be all 0, assuming you're using Dirichlet boundary conditions. Similarly, if you're doing a derivative in the y direction, but the size of the grid in the y direction is only 1, again, you'll force those matrices to all zeros. And so they'll take up almost no memory, because if we're storing these as sparse matrices, very, very light on memory. Don't store those as full matrices.